When an enterprise database attempts to process a massive analytical query on a single machine, inbound data traffic quickly overwhelms the available CPU and memory. For decades, the standard response to this bottleneck was vertical scaling. Database administrators would buy larger hardware, cramming more RAM and a faster processor into a single host server to handle the load. But the mathematics of vertical scaling eventually collapse. When executing a complex query, such as a multi-table join or a group by operation across hundreds of millions of relational rows, a single processor hits a hard physical ceiling. No matter how much memory you install, routing massive data volumes and high-velocity queries through one centralized machine creates a permanent hardware bottleneck. This shift is NoSQL, a category of databases engineered to distribute datasets across a cluster of commodity servers, rather than a single machine. Instead of continually upgrading one monolithic tower, the architecture expands by fracturing into a distributed, interconnected grid of smaller nodes. In a distributed grid, the network cost of joining two relational tables increases as data travels between separate machines. To maintain performance, these systems move away from tabular schemas and multi-table joins in favor of independent, self-contained records. Conquering scale at this level requires two synchronized layers: a clustered physical topology to route the network traffic, and a distributed algorithmic framework to divide the mathematics. Hardware distribution is ineffective if the software cannot utilize it. The core database engine must be capable of shattering a single complex query into thousands of concurrent microtasks. To prevent network saturation, a massive block of unstructured data must be broken down at the source, shattering into hundreds of independent data shards. This process is driven by MapReduce. It is the core software model utilized by NoSQL databases to process and generate massive datasets in parallel. A master node receives a massive query, dividing the task and delegating subtasks downward to individual worker nodes. Each local node then takes its raw data block, filters it, and converts the text into highly structured key-value pairs. This is known as the map function. It ensures that the process of transforming and preparing data happens locally on the individual cluster node, before any information is transferred over the network. By forcing nodes to process only their local slice of the data, the map function bypasses the central memory constraint. No single machine ever has to load the entire dataset into its RAM. Once the data is mapped, an automated routing layer intercepts the output. It identifies dispersed key-value pairs sharing the exact same key, grouping them together. These collected keys are routed to a reducer node, stacking multiple values into a formatted array. This intermediate step is the shuffle and sort phase. It is an automated network protocol that guarantees all identical keys end up on the exact same physical machine. The reducer node then evaluates that grouped array, applying a mathematical operation to compress it down into a single final output value. This is the reduce function. It executes the final aggregation computation, such as a sum or an average or a count, to condense the large array into the query's actual answer. Through this two-step algorithm, a linear calculation that would take hours to process sequentially on one server is executed concurrently across a network in milliseconds. To implement this algorithmic theory in a production environment, the database requires a physical hardware topology built specifically to route these operations. MongoDB's topology separates routing logic from storage. A query enters, hitting the Mongo's router, the traffic director. Mongo's pings the config servers, which return a map of the exact record locations. Using this, Mongo's forwards the query only to shards holding the targeted documents. To prevent data loss if a shard fails, MongoDB ensures high availability using replica sets. A primary node handles all writes, while secondary nodes continuously replicate the data. This automated sharding approach prevents the routing litter from bottlenecking. It delegates the processing execution directly to the physical hardware where the data lives. While MongoDB relies on designated routing and metadata masters, extreme workloads, like processing millions of IoT sensor streams per second, require a decentralized architectural approach. Apache Cassandra abandons the centralized routing layer entirely, utilizing a masterless peer-to-peer ring topology. Without a master to direct traffic, the cluster manages itself via a decentralized gossip communication protocol. The nodes constantly ping each other, exchanging state and health details in real time. This masterless design eliminates single points of failure. Any node in the ring can natively accept an incoming read or write request from the client. To manage the data internally, Cassandra uses a wide column storage approach. It organizes data dynamically into column families, optimizing analytical read speeds and maximizing disk compression. By trading centralized control for a peer-to-peer network, the database achieves linear scalability. You can expand the ring endlessly, guaranteeing continuous uptime even if multiple nodes fail simultaneously. But if any node in a decentralized ring can accept a write request, how does the system guarantee data accuracy when millions of concurrent operations overlap? The answer is tunable consistency. This mechanism allows database engineers to manually configure the balance between operational speed and strict data accuracy, tailored to each individual query. For example, if you are capturing high-velocity data where a dropped packet is acceptable, you prioritize sheer speed over cluster-wide verification. You configure the query for consistency 1. The database requests acknowledgement from just a single node and finalizes the write instantly, accepting the risk of temporary data inconsistency across the other nodes. Conversely, if you are processing a financial ledger where accuracy is absolute, you configure the query for consistency quorum. This forces the system to wait for a majority vote across the cluster before it acknowledges success. Parallel processing at this scale depends on the synergy between the MapReduce algorithm and specialized physical topologies. By moving away from rigid tabular constraints, engineers can dictate the specific physical behavior of their data.